Good morning. My name is Krishna Dev, roll number CHI18002. Today we'll be discussing the preparative methods of boron hydrides, which is also known as borings. Now, before heading towards the main topic, that is preparation of boron hydride, I would like to quickly go through some basic points. The boron hydrides are the compounds of boron and hydrogen. The borings are mainly of 5 types: closo, nido, additiono, hypo and conjunctoboron. Closoboron has the molecular formula BnHn2-. It is dianionic in nature. The nidoboron, having the molecular formula BnHn plus 4, has one empty corner structurally. This type of borane has nest-like structures. The additionoboron, having the molecular formula BnHn plus 6, has two corners empty structurally. This type of borane has spiderweb-like structure. The hypoboron, having the formula BnHn plus 8, has three empty corners structurally, and the last one, that is conjunctoboron, has structures formed by linking two or more of the preceding type of boranes. The boranes are generally diamagnetic, colorless in nature, and has low or moderate thermal stability. The lower boranes are gaseous in nature at room temperature, whereas the higher boranes are highly volatile liquids or solids. Now let us look at the preparative methods, the preparation of boron hydrides. Now at the very outset, I would like to mention the name of a chemist whose name was Alfred Stock. And Alfred Stock pioneered the boron chemistry, the branch of boron chemistry in chemistry. What he did, he produced mainly diboron in two steps. In the first step, he fused magnesium metal, solid magnesium metal, with elemental boron to produce magnesium diboride. In the second step, he reacted magnesium boride with orthophosphoric acid, which produced a mixture of boranes, mainly the B4H10. Then he heated the mixture of those boranes and produced mainly B2H6. Now, in doing so, Alfred Stock faced a lot of difficulties because the compounds, that is the boron compounds, were highly reactive, flammable and hydrolyzed by water. Then Stock developed another technique, that is the vacuum line technique, which were previously unknown. The preparative method developed by Alfred Stock has now been superseded except for making the B6H10. Now, around that time, there was another chemist whose name was S.G. Shore. Around that time, there was a chemist whose name was S.G. Shore. S.G. Shore and his group developed a systematic synthesis method by using the Lewis acid properties of BX3, in which X can be fluorine, chlorine or bromine. Now what he did, he used the Lewis acid property of BX3 to abstract one H- as hydride from the readily available boron anions such as BH4 or B3H8. What he did, he reacted first BX3 with BH4- to produce HBX3- and BH3 boron, which is highly unstable. So it dimerizes into half moles of B2H6. Next, what he did, he again reacted BX3 with B3H8- and produced HBX3 and B3H7. Now here we can consider B3H7 as the polymer of half moles of B4H10 and half moles of B2H4. We can also produce boron directly by dimerizing BH3. This BH3 directly by dimerizing this BH3 to B2H6. Now in doing so, we'll have to we'll have to keep in mind that there should not be any chemical species. This dimerization takes place only in the absence of other chemical species. In the presence of other chemical species, the dimerization is almost impossible. And we should note that the enthalpy of dimerization of this BH3 to B2H6 is around minus 170 kilojoule per mole. Now let us look at some of the preparative methods of closoboron. The synthesis of closoboron dianions BnHn2-, where N lies between 1 to 7, relies principally on thermolysis reaction of boranes in the presence of either BH4- or aminoboron adducts. The yields are very sensitive to conditions like solvent, pressure and temperature. Now here we can see that ET4 and BH4 is the aminoboron adduct, which on thermolysis at 170 to 190 degrees Celsius within 12 hours produces mainly mixture of closoboron, where N is equal to 9, 10 and 12, and it also produces a traces amount of B11H14-, whose IUPAC nomenclature is tetradecahydro-nido-undecaborate 1-. Now here we should notice that the temperature, that is 170 to 190 degrees Celsius, should not be altered, because it is temperature sensitive, and in altering the temperature we may get different product, we may not get the desired boron. That is why we'll have to keep the temperature, between 170 to 190 degree Celsius. Then the next method is the oxidative degradation of BnHN2-. In this process, in this reaction, we will see the formation of lower closoborins from the higher closoborin BnHN2-. What happens here, smaller closodianions can be obtained by oxidative degradation of BnHN2-. The oxidative degradation can be initiated by UV light, heat, or any mechanical stress in the presence of oxygen atmosphere. What we did here, what we have done here, we have reacted the BnHN2-, we have oxidized the BnHN2- closoborin to BnHN2- where N can be 6, 7, or 8. Now here we should note that we can also use THF, that is tetrahydrofuran, or 1,dimethoxyethane in place of ETOH as a solvent, and we can also oxidize BnHN2- by using UV light. Diboron holds a special place in boron chemistry because it is used to produce many higher borons. So let us look at some of the reactions in which diborons are produced. The first reaction is the preparation of diboron by the reduction of I2. That is by the reduction of I2 molecule by sodium borohydride. It is basically two-step reaction in which in first step, sodium borohydride reduces iodine molecule to sodium iodide, BH3 molecule, and hydrogen iodide. Hydrogen iodide in the next step reacts with sodium borohydride to produce sodium iodide, BH3, and H2 molecule. So overall reaction we can write as 2 moles of sodium borohydride reacts with 1 mole of I2 molecule to produce 1 mole of diboron, 2 moles of sodium iodide, and 1 mole of gaseous hydrogen. Now here we can clearly see that 2 moles of boron molecule, which are highly unstable, dimerizes to form B2H6, that is diboron. Here diglyme is a polyether whose IUPAC nomenclature is di-2-methoxyethyl ether. The next process is a reaction of a solid tetrahydroborate with an anhydrous acid. Here we have taken the example of an anhydrous acid to be H3PO4, that is orthophosphoric acid, and solid tetrahydroborate is sodium borohydride. Now, when 2 moles of sodium borohydride reacts with 2 moles of H3PO4, it produces B2H6, that is diboron, 2 moles of sodium hydrogen phosphate, and 2 moles of gaseous hydrogen. Here it should be noted that in this reaction 70% of the yield is B2H6. So it is an efficient way of the production of B2H6. The next process is the reduction of gaseous BF3 using sodium hydride. On an industrial scale, gaseous BF3 can be reduced by directly reacting with sodium hydride at 180 degrees Celsius. The product trapped out as it is formed to prevent the subsequent pyrolysis. In this reaction, we can clearly see that 2 moles of BF3 reacts with 6 moles of sodium hydride in the presence of 180 degrees Celsius to produce 1 mole of diboron, gaseous diboron, and 6 moles of sodium fluoride. Moreover, we can clearly see that the reaction is redox reaction, that is both oxidation and reduction takes place here. Here the boron in BF3 molecule in the left hand side, being at +3 oxidation state, is changed to -3 oxidation state. That means it is reduced. Similarly, the hydrogen atom in the sodium hydride being at -1 oxidation state is oxidized to +1 oxidation state. So overall it is a redox reaction, that is it is an oxidation and reduction reaction. Now some 200 tons per annum of B2H6, that is diboron, is produced commercially worldwide. So we should take care should be taken in all these reactions, because B2H6 is spontaneously flammable as its heat of combustion is very high. As I have already mentioned that Diboron holds a special place in chemistry as it is used to form many other higher borines. So let us take an example. Let us look at an example of reaction in which diboron is used to produce higher borane. Here it is an example in which consists of 3 steps, where the first step is the unimolecular equilibrium dissociation of B2H6. Here B2H6 is dissociated to form 2 moles of BH3 which are highly unstable. In the next step, which is concerted rate controlling reaction of BH3 with B2H6. Here BH3 reacts with B2H6 to produce B3H7 and a mole of H2 gas, where B3H9 is the transition state. And the last step, which is the formation of stable compound. In this step, BH3 reacts with B3H7 to produce B4H10, and B2H6 reacts with B3H7 to produce BH3 plus B4H10, which further reacts to form B5H11 and hydrogen molecule. Here B5H11 is a stable compound. Let us proceed to the last topic, that is the conversion of closoborane to nido and arachnoborane. Now here it is possible conceptually to remove one BH group from a closoborane. I am putting stress on the word conceptually. It is conceptually possible to remove one BH group from B6H62- or any other closoborane, thereby making it tetraanionic in nature, and then neutralizing it by addition of 4 protons gives a new molecule which is a nidoborane. Similarly, when we remove one BH group from a nidoborane, then it produces a molecule which is dianionic in nature, and thereby addition of 2 moles of protons to it produces a neutral molecule which is an arachnoborane. Now here we can clearly see that the molecular formula of a closoborane being BnHn2- satisfies this formula. So it is a closoborane. Next, the molecular formula of a nidoborane being BnHn plus 4 satisfies this formula, because this can be written as B5H5 plus 4. Similarly, this can also be written as B4H4 plus 6, that is BnHn plus 6. So we can say that this is an arachnoborane. Now, as I have already told at the beginning, that closoboranes are the boranes whose molecular formula are BnHn whole 2-, and I have not mentioned any vacancy or any empty corner about closoborane. So we can here clearly see that there are no empty corners, whereas I have told that structurally the nidoboranes have one empty corner. So here we can see that there is an empty corner. Similarly, in this structure, the closoborane, we can see that there are 2 empty corners which I have already mentioned at the beginning. So we can clearly say that this is the closoborane, this is nidoborane, and this is arachnoborane, and that is how we can convert one closoborane to nido and then nido to arachnoborane. So with this I would like to conclude, and for any further reference we can look at the book, there is Chemistry of Elements by N. Greenwood, because whatever I have explained in this video, all the concepts are taken from the book, that is Chemistry of Elements by N. Greenwood. So for any further reference we can look at that book. Thank you.